All right, the central fact is that the average kinetic energy of all of the particles of a certain gas is equal to half times the mass of each of the particles of that gas times the root mean square speed of that gas. Now, this is quite a bit related to what you've seen in physics, which is the kinetic energy of an object is equal to half times mass times velocity squared. Whereas here, instead of using velocity, we're using the root mean square speed. Now, importantly, this average kinetic energy of your particles, this is proportional to the temperature in Kelvin. So let's say that you were initially at 100 Kelvin, and then you went to 200 Kelvin. By what fraction does the kinetic energy, average kinetic energy, change? Well, you should double the average kinetic energy. All right, so what if you go from 5 degrees Celsius to 25 degrees Celsius? Will you be multiplying the average kinetic energy by 5 times? No, you are accidentally using Celsius. What you need to do is use Kelvin. It's all about Kelvin. Average kinetic energy is proportional to the temperature in Kelvin. So you have, let's see, 278 Kelvin to 298 Kelvin. And so that's only an increase about 10% of temperature in Kelvin, and hence 10% in average kinetic energy of your particles. All right, so it turns out then that the higher the temperature, the greater the average speed of your particles. So, for example, taking a look at nitrogen, in green here you see that at 100 Kelvin, some of your particles, they move very slowly. Some particles move very quickly, but most particles move about around that average speed. There's a range of different kinetic energies and a range of different speeds for each particle because the particles are continually colliding with each other, exchanging kinetic energy. And so by accident, one might briefly get a high kinetic energy. By accident, one might briefly get a low kinetic energy, and others will be around that median. But you see that you're going to have a shifting to the right in speed and kinetic energy if you have an increase in the temperature. Now, it turns out that different particles have different average speeds. Turns out that even though all of these gases at 300 Kelvin, they all have the same average kinetic energy. However, they have different speeds. They have different speeds from each other because though they have different kinetic energy, the same kinetic energy, they have different masses, and hence they must have different velocities, or root mean square speeds. You see that chlorine, which has a molar mass of 71 grams per mole, has a relatively low speed compared to nitrogen, which has a molar mass of 28 grams per mole, which is relatively slow compared to helium, which has a molar mass of 4 grams per mole. Overall, we can see that as we increase the mass, we decrease the speed of our particles. In fact, this is described within this equation. The root mean square speed for a certain element is equal to the square root of 3 times R, that's the gas constant, 8.31 joules per Kelvin mole, times temperature in Kelvin all over molar mass. If you increase the molar mass, you'll decrease the speed. Although it's actually not a linear function, it's to the square root. All right, so considering that, how many times faster does hydrogen travel than helium? You could use this equation and find the root mean square speed for both elements using the molar mass. However, I'd like to set up a more useful equation, which I'll use far more often. You see that at the same temperature, these two gases have the same average kinetic energy for their particles. Hence, substituting in for average kinetic energy half times the mass times the root mean squared speed squared, we can rearrange and get the root mean square speed squared of hydrogen over the root mean square speed squared of helium is equal to the mass of the helium over the mass of the hydrogen. And taking the square root of both sides, you can get this equation. You can see that hydrogen, which is the lighter one, and usually we'll be putting the lighter one on top, it travels faster than helium, which is the heavier one. How many times faster? Take the square root of the mass of helium on top here, although it was on bottom here, over the mass of hydrogen on bottom here, though it was on the top here. That gives us the square root of their molar masses. The molar mass of helium is 4 grams per mole, and hydrogen, H2, is 2 grams per mole. The square root of 2, or hydrogen travels 1.41 times as fast as helium. Wait, does that make sense? Let's see. Hydrogen, it has a molar mass of 2 grams per mole, and helium has a molar mass of 4 grams per mole. Hydrogen is actually twice as light as helium, yet it doesn't travel twice as fast. It only travels the square root of twice as fast. If you're twice as light as something, you actually will travel the square root of twice as fast. So let's say that you were 4 times lighter than a certain particle. How many times faster would you travel? You would travel the square root of 4 times faster, or you would travel 2 times faster. Thanks for watching, guys.